Nah. Greetings and welcome. Today we're talking about measures of variability. All right. So we're used to these ideas of measures of central tendency, right? The averages of a list, right? The idea of finding the middleness of the list of data we have. But that's not necessarily the only quantity that we'd be interested in. Variability is kind of talking about how is our data spread out? How is it dispersed within our list? All right. And you know, where is it densely populated within our list? Because that is equally valuable to us rather than just knowing the middle number, right? So we actually know a measure of variability here. I have a chart I'm going to pull some data from periodically. Actually, I'm going to re-snap this whole thing since I had to piecemeal it together. This chart is a portion of a larger chart presented from the 2012 White-tailed Deer Harvest Report distributed by Vermont Wildlife something, blah, 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 blah. Right? So this is from 2012 stats, and here's the W towns from Windham County. Wilmington represented right there. And this is just the number of deer harvested for each of the seasons respectively. So wow, Wilmington representing with the muzzle loading. Wow, 3 compared to, that's all those other W towns combined. Man, so if we ever get attacked by some redcoats, Wilmington knows how to fight to defend itself with the muzzle loaders. So the first measure of variability, does anyone remember what the range is in terms of statistics? Yeah, highest minus the lowest, right? And that is a type of variability. It's telling me how spread out my data is, the extreme most values of the data and where it's located, right? So let's actually, for my little chart here, let's find the range of each season. Okay, so the range for let's see, archery season, the highest number is 7 and the lowest number is 0, so the range is 7. Right? For the youth season, the highest number is 5, the lowest number is 1, so the range is 4. For rifle season, the highest number is 20, the lowest number looks like 6, so the range is 14. And for muzzle loading, the highest is 3, the lowest is 0, so the range is 3. So I just want to point out that that represents how spread out the data is. So if we compare that to, say, the mean, which is measuring the center, number, or the middleness of the list, right? So 7 plus 7 plus 5 plus 1 plus 0 divided by 5. The mean for this one is 4. The mean for that one is 1 plus 1 plus 1 plus 3 plus 5 divided by 5 is 2.2. Right, so I get the middle number and I have the range. The range measures how spread out it is, and the mean is an average, right, measuring the center of the data. So 67 divided by 5 is 13.4. And then 1 plus 1 plus 1 plus 3 divided by 5 is 1.2. So what I want to point out is I could actually have the same range for some of these lists, but different averages. Okay, for instance, if I let's actually talk about this range of 7. Let's say I added some more data, 3 other towns, and let's say they had 7. That's a terrible color. 7, 7, and 7 were their values. The range would remain unchanged, right? Because 7 minus 0 is still 7, but the mean would have been increased. Okay? Because all of these were bigger than the current mean, and they would have therefore brought it up. So I just want to point out that the range isn't caring about where the middle of the data is. It's just saying how spread out is it, right? And it's not even, range technically isn't telling us how densely populated the data is. If I had all of these 7s, I would say this is really top heavy the way this data is set up. It's just telling me how spread out it is. And we'll actually end up having some other types of means, measures of variability, to describe how spread out our data is. So the first of which is going to be a box and whisker plot. Box and whisker. I believe you guys have probably seen these before. Box and whisker plot. And a box and whisker plot looks like the following, where I would have a number line, all right, and then I end up having a graph above the number line. So the first thing I would plot above the number line is the median, all right, and that's actually also going to be called quartile 2. We'll talk about quartiles in a minute. So I'll call that Q2. So the median is the middleness of, right, the very middle number, or the average of the two middle numbers. And now once I find the median, I'd end up finding the median of the first half of the list. Okay, so let's say that's like located here maybe. And this would be called quartile 1. And then I'll find the median of the second half of the list. So let's say that's like here. It's quartile 3. And these 3 portions make up my box. I end up drawing a box around those things. And now you probably are wondering, well, what about the whiskers? Well, the first whisker is represented by the lowest value. And the top whisker is typically represented by the highest value. So highest. Typically. Technically, sometimes those can be different if there's actually this concept of an outlier. If I have a data point that's like so far away from the rest of them, and there's actually a way, we'll calculate that in a moment, this would be called an outlier, where it's just like, it probably was some error in the data, like something went wrong, likely, and we don't, it would skew our numbers a lot, so we end up actually ignoring outliers, whether they're too high or too low. Okay? And so quartiles, all right, divide our data into groups, all right? So a quartile divides the data into 25% chunks or groups. Okay? So what this means is this is a visual representation of where my data is. And each of these areas, there's 25% of my data there, there's 25% here, there's 25% here, and there's 25% here, ignoring the existence of outliers. All right. So let's actually write that down. So 25%, 25%, 25%, and 25%. So notice what that does for me is now visually I see where my data is densely populated. Right, so this would be like if the data is kind of spread out. Here it's even more spread out. And then here it would actually be really tight and clustered together because it's a smaller area, but it still is 25% of the data. So you could imagine like my data would be really clustered in there, and then here it's maybe, you know, moderately spread out. Maybe that was too many points there, something like that, bam. So you can actually see that it's the smaller areas, it's clustered, the broader areas, it's spread out, and that's giving me an idea of how densely populated my data is, right? And that's a value in measurement. That's something that's worth quantifying. So the ends, by the way, are also sometimes called hinges. Hinges, by the way. So so this is a box and whisker plot, and the idea is that you'd have some sort of number line here. So these locations are not arbitrary; they are very specific. So, for instance, maybe my lowest number was 55. Maybe my highest, or maybe my real highest over here is 100. But maybe the rest of the students, maybe the best they did was like 80 or something like that. And this was like my midterm grades. And I'd say, well, I had a lot of students score, say, between whatever these values were, and that might be interesting to me. Or I could say 50% of my students scored beyond whatever this location would have been, right? So you could actually kind of analyze it and all sorts of stuff like that. Now, with quartiles, we actually have something called an interquartile range. I guess I'll write this. Yeah, I'll write it in green. Interquartile range. All right, which is actually going to be the distance between quartile 3, and quartile 1. So Q3 minus Q1. All right. So it's basically the range where 50% of our data lies, right? So it's that distance instead of the regular range, which is just the top number minus the lowest number. And then there's also this concept called the semi-interquartile range. Which is going to be the kind of, I guess, average distance between the average distance of either of those two chunks. So it's going to be Q3, well, not quite, I guess, or half the distance between those two chunks, which I guess the semi-interquartile range would end up being kind of like this distance. All right. So it's not actually where your quartile lands, right? It's just letting you know where the middle of your data kind of exists there. And there's actually a symbol to represent the semi-interquartile range. It's also referred to as Q sub r. You could say is equal to Q3 minus Q1 all divided by 2. And you might say, well, what's the value in the semi-interquartile range? It's just more ways of analyzing kind of the distribution of our data. And the thing that we use semi-interquartile range is in calculating whether or not an outlier exists. All right, so outliers, let's see. I'll define this for us. Outliers are extreme values that are more than 1.5 times, it seems like a very arbitrary fact. Okay, oh, I was mistaken. I thought it was going to be the semi-interquartile range, but it's no, 1.5 times the plain old interquartile range. Beyond the upper and lower quartiles. Or upper or lower, I guess, technically, because it won't be both. So for this problem, this little visual here that I have, let's say my Q1, let's say exists at, I don't know, maybe it's like 63 or something like that. And let's say Q3 exists at 72. So what would the, let's just do an example. So if, like I said, Q1 is equal to 63 and Q3 is equal to 72, what is the interquartile range for this? Yeah, 72 minus 63. So that's what, 9 is it? And how do I know whether or not I have outliers? Where would my outliers have to be? Well, they'd have to be 1.5 times this value. So 1.5 times 9. Let's see, so that's 3 halves, so that's going to be 27 halves. I guess I'll give it as a decimal. It's 13.5. 13.5 units beyond the upper or lower quartile. So I want to point out visually, it's not beyond this value, it's beyond this value. All right? So 1.5 times the interquartile range from there, and 1.5 beyond the interquartile range from there. Okay? So I would be interested in 63 minus 13.5 or 72 plus 13.5. Right? So 63 minus 13.5 is going to be 49.5, and 72 plus 13.5 is going to be 85.5. So basically any data that, or a single data point that is less than that or more than that would be considered an outlier. Would be less than 49.5 or greater than 85.5. All right, so that's how I would determine whether or not a point was an outlier. Okay, kind of abstract, right? Kind of weird, but that's the idea of how that works out. So yeah, once again, the idea today is visual. This is a visual representation of how our data is dispersed. Range is a number, a single number that talks about how widely our data is spread out. So instead of the middleness, we're talking about how widely spread out it is. And the last concept we're talking about today, all right, it's not the, actually I'll go over to the other side here, is mean deviation. Mean deviation. And we'll actually do some work in Excel in a moment on this as well. So this mean deviation is going to be a number, all right? So it's just a quantifiable number, and it's going to describe how spread out the data is in a very specific way. Is mean. What does mean mean? Well, that's the type of average. And deviation, right, is talking about how dispersed or how much our data deviates from the mean. So this is actually going to be the average distance the data points are from the mean. Okay, is the definition. Now calculating that is going to be a little bit weirder, but I'll give you a formula. So mean deviation is equal to, well, it's an average, so I'm going to have to find the sum and divide by the number of data points. So I'm going to multiply by 1 over n, right? So that's dividing by how many data points I have. And I'm going to have the sum, all right? and I'll start with I equals 1 to n. So I'm going to go through each of my data points. But instead of just, if I did xi here, don't write that part yet, this would just be straight up mean. But I'm not interested in the mean. I'm interested in the average distance my data was from the mean. So instead of finding this, I want to figure out, take my data point and subtract the mean from it. All right. So if my average was 4 and my data point was 7, that distance would be 3, right? So I'd have 7 minus 4. But this is a difference currently. To get a distance, I want it to be positive. So I'm going to actually absolute value that difference to make it a distance. All right, kind of craziness, I know. So let's do some example here. Find the mean deviation. So the average distance that our data is from the mean. Let's see, which one should I pick from our chart here? Let's do of rifle harvests. All right. So we'll specifically look at this. All right. So let's program this up in Excel. And I'm hoping that this will actually communicate the formula to us better. So let's see. So here's my data or my list or whatever. So I'm going to have what? 6, 15, 20, 15, and 11. All right, so there's my list. And actually, let's scroll up here to look at the formula as well. So in Excel, well, first of all right, I will need to know how many data points I have, right? Because that's what n is. So I'm going to do equals count, and I'm going to count everything from A3 to let's say 103. So that's going to allow me to have up to 100 values. All right, so there's my n right there. That's 5. I'm going to want to figure out what the mean is. So x bar, right? I need to know what x bar is. And this isn't a frequency distribution. I actually know the values. So the mean is just going to be the average of this list. A3 to A will go up to 103. So we can possibly enter data in later. All right, so x bar is the same as mean. So the mean is 13.4. Mean measures the middleness of my list. Mean deviation is going to talk about, on average, how far out is my data spread from that middle number. Okay, now watch this. I'm intentionally going to make a mistake with Excel. Why is my x bar all different? Yeah, look at this. This one's finding the average of just those 4. This one's finding the average. Yeah, I have to dollar this, right? I have to make this an absolute reference so that it's always going to be referring to the same cell. So now when I drag this down, you can see that even here, it's referring to the same list, right? Even here, it's referring to the same list. So that's called an absolute reference in Excel. That's an Excel thing. It's good stuff, right? So that way I didn't have to program the formula in 5 times or 10 times, right? It's always going to be the same. So, okay, so I have x bar here. I'm ignoring the sigma right now. The next thing I'm interested in is I want to take each data point and subtract the mean. So I'll call this x minus x bar. So how do I program that in Excel? Well, here's my data point, and I want to subtract x bar, right? Does that make sense? So there's that. There's the difference, but that is not currently a distance. All right. Now, question: what do you think the average of this list would be? Yeah, let's check out what happens here. What's that mean, guys? This is computer speak for it's basically 0. All right, it has to do with rounding. This means 0.0 and then it has 15 zeros, and then 35527. That's computer speak for, as far as you're concerned, that's 0. All right. So that's very intuitive. So I just want to point out, if I didn't have these absolute values, the average of these differences would have been 0, because some of them are above the mean, some of them are below the mean, and that has that seesaw effect where they balance each other out, and it's 0. So that's why I'm interested in the absolute value of x minus x bar, all right, which there actually is an Excel formula, abs, right there. And what's it say? It says, just give me a number, I'll give you the absolute value of that number, all right? There's the number I want the absolute value of. It's just going to make it positive, right? So bam, there's that. So now I've got the absolute value of those differences, which means that's a distance. All right, so this is the distance from the mean, is what that actually is representing. All right, this data point, 6, was 7.4 units from the mean, which was 13.4. 20 was 6.6 units from the mean, which was 13.4. 15 was really close to the mean. It was only 1.6 units away. So to measure this variability, to measure how dispersed my data is, I'm interested in what is the average of these distances. All right, and that's actually what we're going to be talking about. So that now that I know the distances, I want to find the sum of this list. That's what that sigma is meaning. So this formula is going to be equals sum of D3 to, I'll go to down to D103 so I can enter more data later. And so that is the sum of all of my distances from the mean. And now I'm almost there. To find the mean deviation, what's it say? I'm going to take that sum and do what with it? Multiply by 1 over n, or that's the same as dividing by n. So that's going to equal this guy, and I'm going to actually make that an absolute reference. So I'm going to say $D $1 divided by this guy, and I want that to be an absolute reference as well. So when I drag this down, it'll always be the same. So what does 3.92 represent? That's saying that the average distance from the mean is 3.92. All right. So if my mean deviation was really small, so if I had a data set that was still had an average of 13.4, but my mean deviation was like 0.5, I would interpret that as saying my data is super close to that mean. Right? It's only like on average a half a unit away in either direction. Whereas if I have a mean deviation that's like 30, I'm saying, okay, so my average is 13, but my data is spread out on an average distance of 30 units away. It's saying it's really spread out. Okay, so that's what mean deviation is describing, is how spread out our data is. So 3.92 would be the mean deviation of this list. All right, and I'm going to make this Excel spreadsheet available to you guys in a Google Doc for that. And let's see, now that I've got it programmed, I could actually plug in all those other values, but I think I'm just about out of time. I'm actually going to pretty up this Google Doc so that these formulas would automatically be calculated down, and they'll show up blank instead of errors when I have that. And I'll share it with you guys tonight in an email. So thanks for watching, Internet friends. Measures of variability. How far is the data spread out? Blah, blah, blah. Bye-bye.